Subscribe now.
Hello my dear children, today is 14th March, it's Holi today, wish you a very happy Holi and welcome back to the lecture series of Aldehyde, ketones and carboxylic acid, Maharashtra Board Grade 12 Chemistry. This is part 8 of the same video where we are going to continue with the chemical properties of aldehydes and ketones. In the previous video we completed with haloform reaction and aldol condensation. Today we are going to start with 𝐒𝐥𝐤𝐤 reaction. My name is 𝐒𝐵𝗶𝗃𝗏 and you are watching 𝐒𝐵𝗶𝗃 classes. Let's get started. So, 𝐒𝐥𝐤𝐤 reaction is a very important topic again where aldehydes, no ketones, okay, only aldehydes having no alpha hydrogen atom. So, if you remember in the previous reaction in aldol, we had the criteria that aldehydes and ketones which have alpha hydrogen atom, they will go for aldol reaction. Here the criteria is different. Here aldehydes which do not have any alpha hydrogen atom undergo self-oxidation and reduction reaction on heating with concentrated alkali, and this reaction is called as 𝐒𝐥𝐤𝐤 reaction. So first of all, there is no alpha hydrogen atom and hence ketones won't be able to show 𝐒𝐥𝐤𝐤 reaction because ketones will be having alpha hydrogen atom, right? By any chance, I mean you cannot have ketone without alpha hydrogen. So if you see, we take a simple ketone C. This is a simple ketone, that is acetone. This is our functional group, okay, and this is alpha carbon, this is alpha carbon, so it has 3 plus 3, 6 alpha hydrogen atom. So ketones will definitely have alpha hydrogen atom and hence will not show 𝐒𝐥𝐤𝐤 reaction. So aldehydes which are having no alpha hydrogen atom, they will undergo self-oxidation and reduction in presence of concentrated alkali, okay. This alkali could be NaOH or KOH and this reaction is called as 𝐒𝐥𝐤𝐤 reaction. Now see, this is what formaldehyde, this HCHO is called as formaldehyde. This is first molecule and this is the second molecule of the same aldehyde, okay. This is also called as methanal, the IUPAC name is methanal, okay. Now this is reacting with NaOH. Now this will be, the aldehyde will be undergoing self-oxidation and reduction. Now this type of reactions are called as disproportionation reaction. The other name of this reaction is disproportionation reaction. We have done this in redox reaction in 11th standard, where disproportionation means where the same molecule will get oxidized also and reduced also, then that particular reaction is called as disproportionation reaction, okay. So now here, if aldehyde gets oxidized, what do we get? We get carboxylic acid, okay. So one molecule will get oxidized to give you carboxylic acid, and when aldehyde get reduced, what do we get? We get primary alcohol. So if you remember this chain, primary alcohol, okay, primary alcohol on oxidation gives you aldehyde, and aldehyde on oxidation gives you carboxylic acid, carboxylic acid, okay. You remember this chain, so the reverse process will be reduction. So when aldehyde will reduce, it will give you primary alcohol. When it oxidizes, it will give you carboxylic acid. So one molecule of aldehyde will get reduced and the other molecule will get oxidized, okay. So now what is happening, see, this hydrogen, now in short basically what do you do is, this hydrogen you put with this carbon, okay, and this HCOONA. So this hydrogen is converted into this hydrogen is attached with this carbon. So what you are getting is, and another hydrogen, this hydrogen suppose is attached with this oxygen. In short, you remember like this, but basically one molecule gets oxidized. So one molecule gets oxidized, you get the carboxylic acid of the same aldehyde. So HCOOH, this is a carboxylic acid, okay. Now here in place of H, you will be getting the sodium salt of carboxylic acid because we are treating this with NaOH. So we get sodium formate. It is a sodium salt of carboxylic acid. So one molecule gets oxidized, other molecule will get reduced. So you will be getting CH3OH. Okay, now see what did I tell you? This hydrogen you attach with this. So it is CH3, and this hydrogen you attach with this oxygen OH. So you get methanol, or this is called as methanol. Okay, and this ONA gets attached to this carbon. So you get HCOONA. Okay, so this is sodium format. Sodium format. So basically what is happening? One of the molecule is getting oxidized to its corresponding carboxylic acid, and the other molecule is getting reduced to its corresponding alcohol. This is what is called as Carnot-Zaro reaction. Okay. Another example we take, this is benzaldehyde. Benzaldehyde, another aldehyde, aromatic aldehyde without alpha hydrogen atom. So we will take two molecules of benzaldehyde in presence of KOH. KOH is the alkali here. MeOH is the solvent, methanol. This is MeOH, which is methanol heating. So one of the molecule will get converted into its alcohol. So benzaldehyde, the corresponding alcohol will be benzyl alcohol. So you get CH2OH. This is the corresponding alcohol of benzaldehyde, and the other molecule will get oxidized to potassium salt of benzoic acid. Benzoic acid is the corresponding acid. The salt of it, potassium salt of it, because we are using KOH. So we get potassium salt of benzoic acid, which is COOK. So this is called as potassium benzoate, and this is called as benzyl alcohol. Okay, this is your Carnot-Zaro reaction. So now we talk about the crossed Carnot-Zaro reaction, where we take two different aldehyde. Okay, two different aldehyde without any alpha hydrogen atom. So suppose if I take HCHO, that is formaldehyde. One of the aldehyde is HCHO, formaldehyde. The another aldehyde is another aldehyde is benzaldehyde. Okay, so we have taken formaldehyde and benzaldehyde. Both of them are having no alpha hydrogen. They don't have any alpha hydrogen. We have done separately self Carnot-Zaro. Now we are doing cross Carnot-Zaro, so we have taken two different aldehydes. Now in presence of alkali, that is I am taking NaOH, dilute alkali, okay, and we are heating it. So again the same thing, one molecule will get oxidized and the other molecule will get reduced. Now here which one will get oxidized and which one will get reduced? So remember that the one which is having lesser molecular mass will get oxidized. What did I say? The molecule which has lesser molecular mass will get oxidized. So here formaldehyde is having lower molecular mass, so that will get oxidized to formate, sodium formate. So you get HCOONA, and another molecule, that is benzaldehyde, will get reduced to benzyl alcohol. So we get benzyl alcohol. This is called as crossed Carnot-Zaro reaction. Okay, I will write down the name of this molecules. This is formaldehyde. This is benzaldehyde. This is sodium formate. And this is benzyl alcohol. So this is our Carnot-Zaro reaction. Prepare this very well. Prepare a short note where you should write about the self Carnot-Zaro as well as it is a cross Carnot-Zaro reaction. Do not forget to mention that it is a disproportionation reaction. Now the next reaction is reduction reaction of aldehydes and ketones. There are two reduction reactions. One is called as 𝐒𝐿 reaction. The other one is called as Wolff-Kishner reaction. Very important. Both the reactions are very close. I mean, only the reagent is different. You have the same substrate, you have the same product, only the reagent is different. Okay, both of them are name reactions, so you need to prepare it very well. 𝐒𝐿 reaction is what? Where the carbonyl group is what? CO. This is called as carbonyl group. Carbonyl groups of aldehydes or ketones, they are reduced to methylene group. What is methylene group? CH2. So basically your CO group will convert into CH2 group. That's all. The oxygen, one of the oxygen will be replaced by two hydrogens. Addition of hydrogen is reduction, so this process is reduction. So in 𝐒𝐿 reaction, we have zinc amalgam and concentrated HCl. This is the reagent for 𝐒𝐿. So whenever over the arrow, if you see this reagent, zinc amalgam and concentrated HCl, you understand it is Clemmenschen reaction, and wherever you have your CO group, convert it into CH2 group. That's all. Okay. So basically this reagent gives rise to 4 nascent hydrogen. 2 hydrogen you just write down here. 2 hydrogen will be they will substitute the oxygen, and the replaced oxygen and another 2 hydrogen will give you water molecule. Okay. Let us take one example. CH3COCH3. This is called as acetone. Now acetone plus this reagent, which is giving rise to 4H. So this CO group converts into CH2. So your product is CH3, CH2, CH3. That's nothing but propane, and 1 molecule of water is formed. Okay. See another example, CH3, CH2, CHO. This is called as propanal. Aldehyde with 3 carbon atom, propanal. So this oxygen will be substituted by 2 hydrogen. So CH3, CH2, CH3, CH3, CH2, CH3. That's your propane with 1 molecule of water. So this is called as Clemmenschen reduction reaction. Another reduction reaction is Wolff-Kishner reduction. As I mentioned that Clemmenschen and Wolff-Kishner, you have the same substrate, you have the same product, only the reagent is different. So here the reagent is hydrazine. See, this is hydrazine followed by sodium or potassium hydroxide in high boiling solvent like ethylene glycol. This is the reagent. So you have the same substrate. This is your carbonyl group. Okay, hydrazine is NH2, NH2. Now you know that when hydrogens react with carbonyl carbon, H2O molecule is removed from here, and you get a product like this. This is called as hydrazone. This product is known as hydrazone. Now this hydrazone is treated with KOH, okay, along with heating, and this is ethylene glycol. This is a solvent. This is CH2OH, CH2OH is called as ethylene glycol. This is the name of the solvent. Okay. So what happens is this entire thing converts into CH2. So basically what is happening, the CO group converts into CH2. Here we are showing the conversion in 2 steps. In the first step, you have a hydrazone compound. This reaction also we have done. This is a nucleophilic addition of ammonia derivative, if you remember. So this is in removal of water is taking place in the first step, and followed by when you treat this hydrazone with KOH and ethylene glycol, then this entire group converts into CH2. Actually, H2 comes here instead of this entire group with the liberation of nitrogen gas. Okay. Let's take example. This is C2H5CHO, that is propanal. First of all, the water molecule will be removed, and you get C2H5CH double bond N NH2. This is propanaldehyde hydrazone. Propanaldehyde hydrazone. Okay. Now followed by treatment with KOH, ethylene glycol, heating. So what happens is this entire thing converts into H2. So you get C2H5CH3. That is nothing but your propane. CH3, CH2, CH3. This is your propane with liberation of nitrogen molecule. So basically what is happening, this O is replaced by 2 hydrogens. Okay. You get an alkane in this case. Similarly this one, this compound, okay, this is called as this is benzene ring, this is C2H5, this is CO, and this will be called as 1, 2, 3. This is 3-phenyl. 1, 2, 3. 3-phenyl propanone. Okay. So H2O is removed first. You get a hydrazone like this. This is a hydrazone product. I'm just writing hydrazone. This is hydrazone product followed by KOH, ethylene glycol, heating. This entire thing will convert into H2. So you get this compound. Okay, this is a compound here, and so this is called as propyl benzene. C2H5CH2. This is propyl group. So propyl benzene is the name of the compound along with liberation of nitrogen molecules. So this is called as Wolff-Kishner reduction. Now the last reaction of aldehydes and ketones, that is aromatic aldehydes and ketones, which is called as electrophilic substitution reaction. So aromatic aldehydes and ketones, they undergo electrophilic substitution reactions such as nitration, sulfonation and halogenation reaction. The aldehyde and ketonic groups are electron withdrawing group. So something which is electron withdrawing group means it will withdraw the electron from the ring and it will be a meta-directing group. Okay. So whenever you do the electrophilic substitution reaction, the incoming electrophile, it will enter in the meta position of the aldehyde or ketone. So here the nitration is shown. We know that concentrated HNO3. This is nothing but nitric acid. Okay. This is HNO3. If you see, it is written like this, HNO3. It is nitric acid. Okay, concentrated nitric acid and concentrated sulfuric acid is called as nitrating mixture, which gives rise to NO2 plus electrophile. So this is benzaldehyde, and this two mixture, the mixture will produce NO2 plus electrophile, which will enter in the meta position. This is the first position, this is ortho position, this is meta position. So we get meta-nitro. This compound is called as meta-nitro-benzaldehyde. We get this product here, meta-nitro-benzaldehyde, along with liberation of water molecule. Okay. So along with this reaction, we have completed the chemical properties of aldehydes and ketones. Now in the next video, we are going to start with the chemical properties of carboxylic acid. Thank you so much. If you find these videos beneficial to you, please subscribe this channel and press the like button. Thank you. Stay tuned.